this computer. Okay. So I'm going to continue with this chapter. What is left from chapter 25? I said that I'm not going to prepare new offline videos unless I feel good about it, because I'm going to reuse the ones that I had prepared last year. What else? We have like 2 weeks to the midterm. So this is going to basically contain the electric part, actually. Well, I can stop either at chapter 25 or chapter 26. I haven't decided that yet, but chapter 26, there are some certain capacitor discussion, RC circuit discussion in there we have to make. So if we make it in time, then I'm also going to include that thing to the first midterm, right? So it definitely includes chapter 25, but it may also include some parts of it, chapter 26, right? Just keep this in mind. What else? These are the benefits of having a very late midterm date, which means that it contains lots of chapters. And that's actually kind of good, because for the second midterm, we will be basically concentrating on these magnetic things, which are actually a little bit more difficult than the electric chapters. Okay, so in any case, most of the homeworks are actually assigned. I'm going to assign the homework for chapter 25, but I need to transfer these to the new version. So in the old version, I used something called calculated question. Probably you're going to see an example of that problem in one of the homeworks. But this is inconvenient for many reasons, because it only just accepts numbers as in the box, and a lot of people have difficulty with this. So as a result, I need to translate them to the stock form, actually. So that's what I'm doing right now. Okay, so I'm going to prepare OHW 25 and probably 26 as well in the coming days. Okay. So I think before the midterm, I'm going to open all of them, but some of the deadlines will be after the midterm. Okay, just keep this in mind. Okay. So we will be talking about this microscopic, let's say, events. What we were talking about, it was actually current and whatever, the electric fields and things like that. And then we have said that there are these macroscopic form of these quantities, where macroscopically you're interested in the current and the potential difference, but microscopically you're basically looking at this detail in here. So there's some kind of take a point somewhere in here. So let me kind of show it like this. All right. So we have a small region in here. If we just magnify it in here, then what we see is like the charges moving around, right? So different charges are moving. And in that case, we should be using the quantity, basically the local current density and the local electric field. And we have to relate these two to each other. So what's the electric field? So let me draw the electric field in here, all right? Okay, right, in the meantime, of course, I'm going to talk about this. So first, let's say it like this. This is the relation between the current density, J, and the average velocity. right? Velocity of charge carriers. All right, so I mean, basically the current results from the motion of the charge carriers. So somehow we should be able to relate the current density quantity to the, well, let's say it like this. This is a kinematical quantity. So we are making a connection with the first semester of that course. Right, you can think of it like this. Let's remember this, the current density is, at least as its magnitude is equal to the current divided by the area. And this is the cross-sectional area in here. But then I have said that, well, this is actually a vector quantity. So there's a direction associated with this. And then we are going to make this vector quantity related to another vector quantity, which is the average velocity. All right, let me say it like this. People actually call this average velocity as the drift velocity. Why? Well, there are some historical reasons. So we could have called it as the average velocity, but people call it drift because of the fact that there are these frictional processes, because all of these charge carriers are actually hitting with, there are some collisions in there, and then so as a result, there is some kind of a friction-like process in there. So in any case, we know that, for example, in metals, the electrons are the charge carriers. So as a result, they are moving in different directions. So there's some kind of a randomness involved in here. So the different electrons are moving in different directions. In any case, but we can then talk about the average of all of these velocities. So that's called the drift velocity. So if you think about it, Vd is just the, I mean, sum of all of these individual velocities divided by the number of charge carriers in a way. So you basically just think about some kind of a region in here, consider all the electrons within that region, find their velocities, and then divide by, that's basically the arithmetic average of the velocities, right? Think of it like that. So when I say average, it's actually that average, right? And the important point in here is, one of the important points is that the electrons are actually moving very fast, but the average velocity is, it's actually much smaller than these typical velocities. So let me write it down like that. So this Vd in here in magnitude is much less than the typical velocity of charge carriers. Okay. Another thing in here, what's the charge carrier? It's basically electrons in metals. But it turns out that, I mean, for ionic solutions, it is the ions, so which contain the positive and the negative charge carriers. But it turns out that even in some solids like semiconductors and things like that, there appears to be some kind of particular excitations that are called holes, which behave like positive charge carriers. So I'm just going to write down this like that. Electrons and holes in, let's say, semiconductors. I'm not going to explain how. Even in metals, we can actually see the charge carriers as positive. I think I'm going to talk about this later. At this point, we cannot say anything about the sign of the charge carriers, except that, somehow they contribute to the current. So in any case, so the positive and the negative charge carriers, and probably the charge carriers of different types, are going to behave differently. They are going to move in different directions, but eventually they produce a total current. And we would like to at least for each charge carrier kind, we would like to see the relationship between whatever the properties of the charge carriers, like their average velocity, the drift velocity, and the current density, okay? So in any case, so that's our job. I would like to express the current density in terms of the average velocity of the charge carriers, right? So we have a quantity in here, so it's called the carrier density. So it's basically the number of charge carriers divided by the volume, right? Since we are talking about the number in here, this is usually a huge number. I believe that this is about like 10 to the 28 for metals, so that the unit is 1/meter cube. So I'm just going to write this thing down like that, but this is usually the best for the best conductors like metals. It can be on the range of, I think, 10 to the 20 as well. For some semiconductors, I think it can even go below that, right? But in any case, these are actually huge numbers for metals. Just thinking about it, so I might even be off with this, but you know that the Avogadro's number is 10 to the 23, and 1 mole of, for example, a metal like I don't know, a copper, for example. A copper is 64 grams, 1 mole is 64 grams. So think about the volume of a 64-gram copper in meter cube. So you're going to get numbers of that range, right? So this is a huge number. So it's the number of charge carriers per volume. We have the drift velocity. Sorry, there's this charge of the charge carriers. I'm going to show it with small q. For electrons, this is minus e. And of course, we have the drift velocity. So that's the average velocity. Okay. Of carriers, of charge carriers. So I'm going to consider only carriers, only one kind of charge carrier. At the end, I'm just going to add their contributions up. And the question is, what's the current density? So I know that the current density is related with all of them. I know that if the charges do not move, there is no current. So therefore, the current density J should depend on this. I know that if the charge carriers do not have any charge, then there won't be any current. Again, current density should depend on the charge. And also the density, somehow, if the density is 0, yeah, whatever. I mean, so based on this idea, you can kind of guess that the current density is actually proportional to all of them. So as a result, the simplest expression that you can write down is just the product of all of these 3 quantities. And it turns out that this is the correct expression. But I'm going to derive this, okay? So the idea in here is this. So that's a very simple picture. So consider a wire with cross-sectional area equal to A. So I'm just going to consider this. I cannot draw a straight line, right? So this is a magnified wire, right? So there are some charge carriers inside, okay? So assume all of them are moving with the same speed. That's just for calculational simplicity, right? So for simplicity, assume that they all move with the drift velocity, okay? But they don't have to have definite, I don't know, regular distributed position. So they can be distributed randomly, but in any case, that's what it is. So I'm going to consider a certain cross section in here. So let me show this with pink. So there's some kind of an surface in here. So let's say it like this. I'm just going to count the number of carriers that cross this surface in a given time delta t. So I'm just going to introduce some new variables in here. So I'm just going to assume that I just wait for this much time and just counted all the charge carriers that cross this surface in here to the other side, and they are moving, right? So as a result, I'm going to count the number of carriers that cross this surface. So multiplying with their charge, I'm going to obtain the charge that crosses that surface. Dividing by time, I'm going to get the current. So I'm just going to introduce these kind of variables, but at the end, they are just going to go away, okay? So what we do is this, okay? So since all of the, I have assumed that all of them are moving with the same velocity. So it appears that if I just consider a volume in here where, sorry about that, the volume is basically, is that volume of that cylinder with a length which is equal to Vd times delta t, okay? So if I consider it like this, in that case, within that time delta t, all of the charge carriers inside this volume would have crossed that surface, and all of the other ones would not, okay? So basically what I'm saying in here is this. Let me show it like that. All carriers within this volume, let's say, will be able to cross the surface in, well, within time delta t, in time delta t, right? In this time interval. These won't be able to pass within that time, okay? So as a result, this is basically the number of charge carriers that crosses. So let's say it like this, the number of carriers, right? Yeah, this is basically what I write for number, right? In any case, so the number of carriers is equal to, therefore, the volume of that region multiplied with the charge density. So it's the volume of that region. So sorry about this. Number density of the charge carriers multiplied with the volume of that region. And the volume of that region is the area multiplied with length. So therefore, this is NA times VD times delta T. Okay. And I don't know if you have any questions about this. So that means the charge that crossed is basically a charge multiplied with this number of carriers, right? So therefore, this is Q times NAVD times delta T. And I know that the current is basically the charge that crossed, let's say that crossed, divided by the time delta T. Yeah, let me say it like this, the time interval in here. So as a result, I'm just going to take this expression and divide by delta T. So the delta T goes away, and so as a result, we get like NQVD times the area. And finally, the current density is basically the current divided by the area. So therefore, this is equal to NQ times VD. Okay. So this gives us the magnitude only And then after that, we just basically guess the form, the vector form, by just looking a few things. So first of all, VD is a vector. Sorry about this. VD is a vector. And similarly, the current density is a vector. Okay, so I know that they are parallel to each other, right? They are either parallel or anti-parallel. So as a result, it's a direct proportionality. So I know that, for example, there is this case in here. So this is a positive carrier case. For the positive carrier, positive carriers are moving along that direction, and the current density is in the same direction. For the negative carriers, carrier case, let's say it like this. In that case, if the electrons are moving along that direction, if the drift velocity is along that direction, in that case, I know that the negative charges are transferred along that way. So that means the positive charges are transferred, in effect, in the leftward direction. So therefore, the current is positive towards left. And so therefore, the current density is towards left in here. So that means for the negative carrier case, the current density and the drift velocity, they are in opposite direction. For positive carrier case, they are in the same direction. Luckily, the formula contains a charge in here, so I can use the same formula for both cases. So the current density, therefore, must be N times Q times VD for both cases. Okay. So therefore, this is the conclusion that I draw. Okay, so let me add this. All right, so I mean, for electrons, therefore, the current density and the drift velocity, they are in opposite direction, as the formula says. So I mean, we can basically make the same statement about the direction of all of these by using the formula as well. So as a result, this is the correct expression for the relationship between the current density and the drift velocity. Okay, let me add this in here. I'm not going to solve any problem in here. So that's the typical quantities. Okay, so let's say like this for a wire. The current is on the level of, I mean, the typical current is on the level of 1 ampere. So this is a typical current carried by a hot wire in our homes. The area is basically about like 1 millimeter squared, right? 1 millimeter squared. So that means this is like 10 to the minus 3 meters squared. So the area is of the order of 10 to the 6 meters squared. So from here, we can get the current density in that case is a typical value of 10 to the 6 amperes per meter squared. Right? I mean, this is a typical value of the current density in a metal. Okay. I have said that N is of the order of 10 to the, 28 per meter cube. So probably I should have checked this, but in any case, I know that the charges are charges of the charge carrier. So these are of basically is the usually is equal to the elementary charge. And so therefore this is like 1.6 times 10 to the minus 19 coulombs. So let's say that this is 10 to the minus 19 coulombs. All right. What else? And we would like to compute the typical value of the drift velocity here. So I'm just going to use this expression. So J is equal to NQVD. So from here, I'm just going to get the drift velocity. So current density is about 10 to the 6, n is about 10 to the 28, and q is about 10 to the minus 19, right? I mean, in physics, we deal with these kind of numbers, the exponential of something. Sometimes these are extremely large and extremely small, but I mean, in those cases, it's hard to give a meaning. It's hard to try to give a meaning to these quantities because they are ridiculously large, right? So in any case, so I get 10 to the 9 in here, so therefore this is like 10 to the minus 3. And the unit should be meters per second, which means like this is 1 millimeter per second. Okay, so that's the typical drift velocity yeah, let me write it down like that. So that's the typical drift velocity. Okay. So as a result, this is one of the numbers that are basically confusing. So this actually a number that turns out to be too small. So the question is then, I mean, if we just on the button of a light bulb, for example, how is it possible that the light bulb immediately lights up? So that's the question in here. I'm not going to answer that question, right? If we turn on a light bulb, yeah, if you push the button on a button for a light bulb, the bulb lights up immediately. Okay, and the question is, how can we reconcile this? How do you write reconcile this with the typical drift velocity being like 1 millimeter per second? All right, so that's the question. So how do we really understand this? So this is the same question in the textbook as well. Yeah, I would like you to think about it, all right? Because the important point in here is actually thinking about it. You will not be able to find the answer by yourself, but you can justify it. Perhaps you can suspect what it is. And eventually, of course, you are going to learn about it, right? So as a result, yeah, the question is, why is this so small, and is this a problem? Okay. So the next thing is this, the microscopic form of the electric, the Ohm's law. So this is the relationship, sorry about this. So if there are, let's say, two types of charge carriers, okay, so for example, there are electrons, they have a drift velocity like that. So let's say VD1, let's say. So these are charge carriers with charges Q1 and the drift velocity D1, and let's say that they have a density M1. And then we have positive charge carriers. So they have a drift velocity VD2, let's say. They have a charge Q2 and their number density is N2, all right? So, I mean, if I apply an electric field to a conductor, if I have both positive and the charge carriers, and in that case, I know that all of the positive charge carriers will be drifted along the direction of the electric field, and all of the negative charge carriers will be pushed in the opposite direction, right? I know that this is the case, so therefore these two have different directions. But in any case, in that case, it turns out that the current density is basically additive. So as a result, it's the current contributed by the negative charge carriers plus the current contributed by the positive charge carriers, they add up. And all I need to do is to basically just write down the expressions of both of them and add them up. Okay, I think this is kind of the simplest situation in here because both current densities will be in the same direction. So let me say it like this. So the electrons will contribute to a current density along this direction. And the positive charges in here will be contributing to the current density along that direction. The total current density is basically the sum of these two. Okay. So, but, I mean, in solid state physics, for example, there are situations where these current densities and the drift velocities do not have to be in the same direction. So sometimes they are moving in some different directions like that. And I don't know, they are moving in different directions like that. They make angles with each other. In any case, in those cases, of course, this vector calculation is going to be important because this is the one that's going to be related to the macroscopic current. In any case, there's just a simple additivity in here. So if there are two types or more types of charge carriers, then you just add the current densities of all of them together. Like that. Okay. So that's the next thing that I want to talk about. The next thing is the relationship between the current density and the applied electric field. Right. This is the relationship between E and J. Right, so that's a situation, as I have mentioned before. So there's an externally applied electric field in here. So E is externally applied. Okay, I know that because of this, the negative charge carriers is going to feel a force along this direction. And the positive charge carriers is going to feel a force in the direction of the electric field, right? Okay. So that means, well, this is just force. So therefore, this is related to the acceleration. So it's not the same thing as velocity. So in reality, though, I know that these are moving with some certain velocity. So for example, this electron might be moving along that direction. So that's the initial velocity. So I know that because of the electric field, applied electric field in here, there's a force and therefore there's an acceleration in here. So therefore this electron doesn't move along a straight line. It just moves along some curved path in here. So as a result, its velocity is going to change because of the acceleration, right? Normally the electric field causes an acceleration. And so therefore it just causes, I don't know, if they have some velocities like that, this is the initial velocity for that one, it will basically accelerate the charge carriers. But in any case, what's important in here is the drift velocity. And the drift velocity is just the average velocity of all of these velocities, all right? And in that case, when we think about the drift velocity, it turns out that this drift velocity appears to be in the same direction as the force. Right? So let me say it like this, the drift velocity, right? Drift velocity. So turns out to be in the direction of the force. Okay, normally if there is no electric field, there's still a velocity in here. All of these initial velocities are there, but their average is equal to 0. If I apply an electric field, in that case, these velocity distributions will change. And this is basically the change in the average velocity that happens because of the existence of the electric field, right? So this is actually a complicated motion because there are collisions in here. So these electrons or the charge carriers actually collide with everything. So this part is actually complicated. So after the collision, they are going to change their direction. And so as a result, they are going to continue this accelerated motion. So because of the existence of the collisions, the physical picture is very complicated. Even in solid state physics, you won't be able to analyze this correctly. So as a result, what we do most of the time is just do the phenomenology, right? You just expect a behavior, and then you just write down the appropriate conditions for this behavior, okay? So there are a few things in here. So the drift velocity, it turns out to be equal to some coefficient in here multiplied with the electric field. So that's basically proportional to the electric field, right? But let's just say it like this. For negative charge carriers, this is opposite. And for positive charge carriers, they are in the same direction. So the coefficient in here is called the mobility. I'm not going to define it with a symbol because we are not going to use it, but this is something that you hear from time to time from researchers, right? So for solid state physics, for example, for semiconductors, mobility is actually a nice figure. It basically tells you the relationship between the drift velocity and the electric field. So let me draw this picture again. Sorry about this. If the electric field is along this direction, for negative carriers, the drift velocity is along that direction. And for positive carriers, the drift velocity is in the same direction as the electric field. Okay. So the second thing, so that's the first thing, which we don't care. The current density is also proportional to the electric field. It's linearly proportional to. In that case, we just write down the current density is equal to some coefficient in here, which we call as the conductivity times E, usually shown with the symbol of sigma, small sigma. Again, I'm not going to define it, but I think the textbook defines it in any case. But we usually write this as the reciprocal in here. We just move it to the left side. So we just write this thing down as something called the resistivity multiplied with J. It gives us the electric field. So rho in here is called the resistivity. It's just the reciprocal of the conductivity. Okay, so that means high resistivity means low conductivity, right? It's that relationship. So I'm going to repeat this picture again, but for the current density. So as a result, if I have an electric field along that direction, I know that the negative charge carriers have a drift velocity like that, and the positive charge carriers have a drift velocity like that. But in any case, for negative charge carriers, the current density will be opposite to the drift velocity because of the charge in there, right? So let's say it like this. For negative charge carriers, we have the number density multiplied with the amount of the charge, their charges multiplied with the drift velocity. So therefore, current density is opposite. So therefore, the current density is in the same direction as the electric field. And similarly for the positive charge carriers, so for the positive charge carriers as well, the current density is in the same direction. So therefore, the resistivity, let's say it like this, resistivity is always positive, independent of what the charge carriers are. And that's the reason why we cannot understand the sign of the charge carriers by just looking at the direction of the current and the potential difference, right? Okay, let me then write this thing down as, sorry about this. So that's the relationship. So it's the rho times J is equal to the electric field. So that's called the microscopic form of Ohm's law. because it gives us the relationship between the applied electric field and the produced current. So there is this macroscopic form. This gives us the relationship between the potential drop and the current in terms of a coefficient that we call as the resistance. So that's the macroscopic form. Of Ohm's law. Okay, so let me try to do it like that. So as a result, let's say it like this: for a wire with length equals, I think I'm going to use L like that, right? And cross-sectional area A. Sorry, sectional area A and resistivity rho. So you know how to do this calculation, but I need to do it at least once. So I have this kind of a wire. So suppose that I have some potential drop between the ends and there's a current in here, right? So there's a potential drop. So V is the potential drop, let's say. I is the current. These are the macroscopic current. Okay. So in any case, if I is positive along that direction, then that means this end is at a higher potential than that end, which implies that the electric field is pointing towards left. Right? There is an electric field along that direction. So what's the magnitude of the electric field? It's basically potential difference divided by the length. What is the current density? Well, the current density is basically current divided by the area. And I know that these two have this relationship. It is rho times the current density is equal to the electric field. And if I insert everything in here, so rho times the current density is current divided by the area. Electric field is the potential drop divided by the length. From here, we then deduce that rho times length divided by the cross-sectional area multiplied with the current gives me the potential drop. And I know that the macroscopic form of the Ohm's law is like that. And so therefore, from here, we just deduce the resistance of a wire with resistivity rho, length L, and the area A. Okay, so that's basically the resistivity of a wire. Let me say with uniform cross-section. Okay. Okay, I think that's it. I mean, we don't have to say anything further in here. We can perhaps do some calculations with it, but I think that's not that important. So you know how the resistance increases with the length and how it decreases with the cross-section area. So by remembering these, you can also remember this formula. Now, I'm just going to say that in offline videos that I have just mentioned at the beginning, I just solved this problem. It's just the resistance of a conical shaped wire. So we have a wire, but the cross section is not uniform, right? So as a result, we have like the radius of that circle is equal to A, and the radius of that circle is equal to B, and the length is L, and the resistivity is rho. Let me write this thing down. And the question is, what's the resistance? Okay, I solved that problem, and I think you can look at the solution in there. So you could have guessed that the resistance is equal to the resistivity multiplied with length divided by some sort of an area, cross-sectional area. But since the cross-sectional area changes, I need to use some kind of an average area, right? But what kind of an average? I need to take the average of this area and that area, but what kind of an average should I use? Is it arithmetic or geometric and whatever? It turns out that this is the geometric average actually. So it turns out this is like, if I remember correctly, it turns out that in that case, I need to use the geometric average of the two areas. It's basically the product of the areas multiplied with the square root, right? In any case, I'm not going to solve that problem because at the end, at least for understanding the physics, solving these kind of problems are not that important. But I suggest that you actually go over the solution because it kind of illustrates some of the ideas. How do you divide the problem into pieces and then join them together and write it in an integral form? So these are actually very nice exercises. A physicist should actually know these kind of calculations, right? So that's the particular reason why you should actually look at the solution of that problem. But I suggest that before that, you actually try to solve it yourself, all right? Okay, so let me stop the video, and if you have any questions, then I'll take the questions.